Welcome to this explainer. Today, we're going to be treating clunky O of n squared time complexity as the ultimate villain to conquer in our whiteboard coding sessions. Seriously, if you've ever felt the absolute pain of an algorithm timing out right when things get interesting, well, you're in exactly the right place. We are going to transform those sluggish nested loops into sleek, highly optimized linear solutions. These are the kinds of optimizations that save critical server costs and keep your apps from crashing when they're hit with heavy user queries. So you might be wondering, why do these O of n scored solutions actually fail in the real world? Well, in a low-stakes environment, writing a quick double for loop to check every possible combination, it feels completely natural. But when your data scales up to hundreds of thousands of elements, that exponential growth in processing time completely breaks down. It's a real bottleneck. We have to train our minds to look for the shortcuts, the mathematical properties and auxiliary data structures that let us bypass redundant calculations entirely. Here is our roadmap for today. We'll start with an intro to array optimization, move into mastering subarray algorithms, tackle 2D matrix traversal techniques, uncover the matrix contribution technique, figure out how to find the next permutation, and wrap it all up with some solid coding interview preparation. All right, let's jump straight into Section 1, an intro to array optimization. Think of this like a banking ledger. Instead of adding up your last 50 transactions every single time you want to check your balance, you just keep a running total, right? That is essentially a prefix sum. By pre-calculating this running total from index 0 up to every other index, array updates over any range become practically instant. You just take the sum at the end of your range, subtract the sum from just before it starts, and boom, you've got your answer. It's amazing to watch an O of n loop immediately turn into a sleek O of 1 mathematical shortcut. Let's keep the momentum going with Section 2, Mastering Subarray Algorithms. If you want to find the maximum possible sum of a contiguous subarray, your brute force instinct is probably to generate every single combination using two nested loops. Kadane's algorithm completely neutralizes that need. Think of it kind of like financial inheritance. You simply maintain a running current sum and the maximum sum you've seen so far. As you step linearly through the array, if your current sum drops below 0, you just reset it to 0. You're effectively dropping the bad debt. But here is a crucial edge case you absolutely have to remember. If all the numbers in your array are negative, you don't reset to 0. You just pick the smallest negative number to minimize your losses. Next up is the infamous rainwater trapping problem. Looking left and right for every single bar takes a massive O of n squared time. So let's build virtual walls instead. In one pass from the left, we record the tallest bar we've seen so far. In another pass from the right, we do the exact same thing. Now look at any bar in the middle. The water trapped above it is simply the minimum of its two virtual walls minus its own height. Just like that, we've traded nested loops for two highly efficient O of n sweeps. Our third major subarray technique is merging intervals. Imagine a completely chaotic list of overlapping number ranges. First things first, you sort them by their starting index. Honestly, sorting is the absolute key to dropping your time complexity here. Then you just step through. If the next interval's start overlaps with your current interval's end, you merge them by updating your end boundary to the maximum of the two. It's exactly like scheduling maintenance by finding the longest gap in overlapping user activity windows. You're taking chaos and cleaning it up into distinct blocks of time, all in a single pass. Okay, let's pause for a quick subarray checkpoint. We've used prefix sums for instant range queries. We applied Kadane's logic of dropping negative baggage to find maximum subarrays. We built auxiliary arrays as virtual walls for trapping rainwater, and we used sorting to cleanly merge overlapping intervals. Notice the pattern? We have systematically eliminated the need for nested loops across the board. All right, Section 3, let's add another dimension and look at 2D matrix traversal techniques. Traversing 2D arrays can quickly turn into a total mess of tangled variables. To traverse a matrix boundary clockwise smoothly, you just need to establish 4 variables: left, right, top, and bottom. Watch how the pointers shift. You walk from the left pointer to the right pointer along the top row. Then move your top pointer down. Walk from top to bottom along the right column. Then move the right pointer in. This turns a visually complex problem into a very strict, manageable set of 4 dynamic boundaries. Now, once you understand that boundary traversal, spiral printing is literally just repeating that same logic layer by layer until the entire matrix is covered. As soon as you finish printing one outer ring, your left, right, top, and bottom pointers have all shifted inward by exactly 1 layer. You just wrap your boundary logic in a while loop. I've got to say, it is incredibly satisfying to code this out visually on a whiteboard. Moving on to Section 4, we're going to tackle the matrix contribution technique. Generating every single submatrix inside a 2D matrix using pointers is a brutal O of n cubed, or even worse. Instead of that clunky brute force method, we can optimize this to O of n times m by calculating exact how many submatrices a single element contributes to. We need to stop looking from the outside in and instead ask ourselves, if I am a single number sitting at a specific coordinate, how many rectangles can actually be drawn around me? Look at the visual overlap here. An element's total contribution is just its value, multiplied by its top left and bottom right possibilities. Let's break that down. For any element at row I and column j, the number of ways to pick a top left corner is strictly I plus 1 times j plus 1. The bottom right possibilities depend on the distance to the edges, so you multiply those combinations together, multiply that whole thing by the element's actual value, and boom! You have its total contribution. No submatrix generation required whatsoever. Time for our 2D checkpoint. Take a breath and celebrate for a second, because we just defeated some very heavy nested loop villains. By manipulating our left, right, top, and bottom pointers, we seamlessly navigated spirals. And by relying on mathematical coordinate counting, we bypassed generating submatrices entirely. We literally turned a massive coding headache into a smooth, single linear pass. Let's shift gears to Section 5, finding the next permutation. I know, finding the next lexicographical permutation sounds absolutely terrifying at first, but it's actually just a purely visual mechanical process that runs in O of n time and O of 1 space. Step 1. Scan backward from the end to find the first number that dips down. That's your pivot. Step 2. Scan backward again to find the smallest number to the right of the pivot that is still larger than the pivot, and swap them. Step 3. Reverse everything to the right of your original pivot index. And you're done. Now what about the edge case? If the whole array is descending, meaning it's already the absolute largest permutation possible, you just reverse the whole thing to reset it back to ascending order. Finally, Section 6. Let's talk about how to use this for your coding interview preparation. We all know the interview room can be incredibly stressful, but following this strategy will literally save the day. Always verbally establish the brute force O of n squared solution first, before you reveal your elegance optimization. Don't just jump straight into Kadane's algorithm in total silence. Explain why checking every subarray is inefficient, and then introduce your running sum logic. Always make sure to test your edge cases, like an array of all negative numbers, and clearly explain how treating a little auxiliary memory is going to give you massive boosts in processing speed. Well, we have covered an incredible amount of ground in this explainer, going from 1D prefix sums all the way to complex 2D matrix contributions. The real secret here is to start recognizing these underlying patterns. So to wrap things up, I want to leave you with this final thought. Take a look at your own projects. Which clunky brute force algorithm in your own code are you going to optimize next? Keep practicing these visual whiteboard techniques, and I'll catch you in the next one.